For decades, the search for life beyond Earth felt like listening to static. Faint whispers buried in cosmic noise, signals that hinted at meaning but never resolved into anything real. Every promising discovery seemed to collapse under closer inspection. Every Earth-like world turned out to be just distant enough, just hostile enough, or just unstable enough to fall short. Habitability remained a fragile idea, a narrow window balanced on perfect conditions that seemed almost impossible to replicate. Then the James Webb Space Telescope changed the conversation. Not with a single dramatic announcement, but with something far more unsettling. A pattern began to emerge. Quiet at first, then undeniable. Across different star systems, different types of planets, and entirely different cosmic environments, Webb's observations began pointing in the same direction. Not certainty. Not proof of life. But convergence. For the first time, multiple independent datasets were aligning. Atmospheres, tapenomana ranges, chemical signatures, and structural stability, all overlapping in ways that suggested something deeper. Instead of isolated cases, Webb revealed clusters of conditions where the requirements for life did not just appear, they stacked. Probability began to accumulate. And that accumulation changed everything. What makes this moment so profound is not just the strength of the evidence, but its origin. These are not distant, unreachable corners of the universe. Many of these worlds were already known, already catalogued, and in some cases quietly dismissed as unremarkable. Now, under Webb's gaze, they are being re-examined. And as each layer is peeled back, a quiet realization takes shape. Habitability may not be rare. It may have been surrounding us all along. If that is true, then humanity's greatest mistake was not failing to find life. It was expecting life to announce itself loudly. Instead, it may have been waiting silently, for us to finally build the tools capable of seeing it. One of the most surprising shifts came from an unlikely place: Ceres. For years, it was treated as little more than a leftover fragment from planetary formation. Geologically interesting, perhaps, but biologically irrelevant. That assumption no longer holds. Spectral analysis revealed widespread salts and hydrated minerals across its surface. Clear evidence that liquid water once interacted with rock, not briefly, but over extended periods of time. But the real story lies beneath the surface. Data now strongly suggests the presence of a vast subsurface reservoir. Not a frozen relic, but a chemically active briny ocean, sealed beneath layers of ice and rock. Protected from radiation. Shielded from temperature extremes. Isolated, yet stable. This environment mirrors some of the most extreme ecosystems on Earth's ocean floor, where life thrives without sunlight. Hydrothermal processes, energy sources independent of stars, may have existed there as well. Suddenly, the question becomes unavoidable. If life can exist in Earth's deep oceans without sunlight, why not here? While Ceres reveals what can hide beneath the surface, another mystery challenges us by remaining completely unseen. Far beyond the known planets, in the distant region known as the Kuiper Belt, objects move in strange and unexpected ways. Their orbits appear stretched, tilted, and oddly aligned, as if guided by something massive lurking in the dark. This hypothetical object is known as Planet 9. It has never been directly observed. But its presence is inferred through gravity, the most reliable force in the universe. Calculations suggest a world several times more massive than Earth, orbiting hundreds of astronomical units from the Sun. At that distance, sunlight is barely a whisper. And yet, if it exists, it could be internally active. Warm beneath the surface. Stable over immense timescales. A hidden world. Silent. Unseen. yet shaping the architecture of our solar system. Webb's sensitivity offers the first real chance of detecting it directly. And if it is confirmed, it would mean something extraordinary. Even our own solar system is not fully known. When Webb turned its instruments toward the TRAPPIST-1 system, expectations were already high. 7 Earth-sized planets orbiting a single cool star. What it revealed was not just diversity, but repetition. Multiple planets showing independent signs of potentially habitable conditions. Not one candidate. Several. Some may host vast global oceans, stable over billions of years. Among them, TRAPPIST-1e stands out as especially compelling, with signs of a balanced environment capable of retaining heat and liquid water. Imagine standing on one of those worlds, looking up, and seeing another habitable planet hanging in the sky. Close enough to feel almost reachable. This system challenges one of our deepest assumptions. That habitable worlds are rare accidents. Instead, it suggests that when conditions are right, nature may produce multiple life-friendly environments at once. Then there is K218b. A world that looks nothing like Earth. Covered not by continents, but by a vast ocean beneath a thick hydrogen-rich atmosphere. Once dismissed as too alien to support life, it is now one of the most intriguing candidates ever discovered. Webb detected water vapor, carbon-based molecules, and atmospheric conditions that could support stable liquid layers. This is not a familiar world. It is a sealed ocean planet, pressurized and chemically active. And it teaches a critical lesson. Life does not require familiarity. It requires energy, chemistry, and stability. Another unsettling candidate is Proxima Centauri b. Orbiting the closest star to our Sun, it exists in a harsh environment dominated by stellar flares. For years, many assumed its atmosphere would be stripped away. But newer observations suggest that it may still retain one. Possibly shielded by magnetic forces or dense atmospheric layers. If life exists there, even in microbial form, it would mean something profound. Life is not fragile. It is resilient. Not every discovery is about habitability directly. Some are about capability. The atmosphere of WASP-39b, a gas giant far too hot for life, provided a breakthrough of a different kind. For the first time, Webb delivered an extraordinarily detailed chemical analysis of an alien atmosphere. Carbon dioxide. Water vapor. Sulfur compounds. Molecule by molecule, the atmosphere was decoded. This planet is not a home for life. But it proves something essential. If biosignatures exist elsewhere, Webb can find them. Other worlds, like TOI 700d, offer something quieter but equally important: stability. Earth-sized planets orbiting relatively calm stars, receiving energy levels similar to our own world. Not extreme. Not dramatic. But steady. And in astronomy, stability is everything. Individually, each of these discoveries might seem like an exception. But together, they form a pattern that becomes difficult to ignore. Hidden oceans beneath ice. Oceans beneath thick atmospheres. Worlds enduring violent stars. Worlds orbiting calm ones. Multiple habitable candidates within single systems. This is not one pathway to habitability. It is many. At some point, the accumulation becomes overwhelming. One planet with water is interesting. A dozen across different systems, environments, and conditions begins to shift the narrative entirely. Webb does not need to detect life directly to change history. It only needs to demonstrate that the conditions for life are common. And increasingly, that is exactly what it is doing. The question humanity has asked for centuries was simple. Are we alone? But that question is starting to evolve. Because when habitability stops looking rare, life stops looking miraculous. It starts looking inevitable. The universe no longer feels silent. It feels patient. And now, for the first time in human history, we may finally be ready to listen properly.